Thank you very much for coming today. I appreciate the audience. And I'm kind of the novice on the team. Lori and Zeb have been working with fire and working in these ecosystems much longer than I have been. I've primarily been working up in northern or northwestern Canada, where we're dealing more with that kind of stand replacing fire regime. So this has been a learning experience working with them for me as well. The work that I'm going to talk about today is definitely a lot of Emma's work. And so Emma unfortunately isn't here today, but Emma's been spearheading the charcoal records that we've been developing from Jasper. And Katrina Moser is another of our investigators on this project. And Katrina's at the University of Western Ontario, and she's kind of leading what happens when we have these fires. What happens to the lake ecosystems in particular? And what does that do with respect to changes in water quality? And so that's kind of another component of this project that we've been working on as well. So for today, how many people have cored lakes before? Okay, so a few, so that's good. So I'm going to talk a little bit about paleoecology and the need for lake sediment studies, and hopefully this will be new to a lot of people in the audience, and as well how we go about recovering lake sediment cores, because it's a fairly straightforward process, but I'm going to talk about the what, where, and how, and then finding evidence for past fires, and in particular I'm going to focus on macroscopic charcoal. And so this differs from microscopic charcoal. You can actually see it with your eyes. We do the work under a microscope still, but it's presumed that macroscopic charcoal represents more localized fires. And Zed had alluded to this earlier in the afternoon, and can we use these records to get at not just fire frequency and whether or not that fire frequency is changing, but as well past intensity? And can we look at the morphology of the charcoal and find out what was burning? And then does that represent potentially different types of fire regimes in the past? And finally, I'm going to talk about some of the ongoing research. Emma, as I said, has been doing a lot of work, and she's got a lot of results already. So I'm going to present some of those results that we have from Jasper and some of the other work that we've been doing in the other parts of the Canadian Rockies around the Nelson area. So why do we need these records? When we think about our knowledge of environmental change, our knowledge from instrumental records, for example, so things like climate records, only goes back in most areas about 100 years. And then you get to places in Europe, for example, where you may be stretching those records back several hundreds of years. But that's quite rare. Most of that stuff lasts 100 years. And in the north, where I do most of my research, we're talking climate records that are only extending the last 50 years or so. We could start to push some of that information about environmental change further back in time using some historical sources as well. So settlement records, Hudson's Bay records, things like that. And so that can stretch us back maybe 3 or 4 centuries, maybe 5 centuries. But then we get into things like these tree rings. And so the tree rings we've heard quite a bit about this afternoon already, but certainly we're talking a lot of tree ring records that go back at least 100 years, and then even some that are pushing close to 1,000 years, and then the odd ones that are even going back several thousands of years as well. But if we really want to go back in time and get a nice long-term perspective of how the environment and how ecosystems have changed, then we can turn to lake sediment. Unfortunately, the resolution of these records is going to change as well. So the tree rings, the tree rings and the instrumental data give us that nice annually resolved records. The lake sediments, not so much. And so we're talking more on the scale of decadal, and if we're really lucky, subdecadal. If we get very fortunate and we get lakes that have annually deposited sediments, then we can get that kind of annual resolution. But those types of lakes are pretty rare. Now, similarly with our fire knowledge, and when we start to think about what we know about fire, we know quite a bit from monitoring over the last several decades, for example. And so this kind of shows this overlap between the knowledge that we have in the monitoring sphere, from hours, where we're talking about fire weather and our knowledge about fire weather, ignition sources and whatnot, to maybe days, and then getting into some of the stuff with the tree rings, where we're talking years and decades, and what's driving the initiation and the starting of fires and burning of ecosystems. So when we think about this from a knowledge base, we have lots of information about those types of temporal scales. But when we get into these longer temporal scales, and what is driving fire in a variety of ecosystems, that knowledge base starts to really disappear. And that's where the techniques of paleolimnology and paleoecology come into play. And so that's where I'm going to kind of focus the remainder of my talk for this afternoon, in that sphere in the bottom. And why is this important? Well, from a variety of perspectives, this long-term knowledge can be very effective in developing this understanding of how these ecosystems function, but as well in developing management plans associated with these ecosystems. And so that paleoenvironmental data that we collect from these lake sediment cores can then go into various models, environmental models. And so these process-based models can use that paleo data, and they can use that paleo data to simulate past changes. And so if they can replicate what they see in the paleoenvironmental data, then we assume that those process-based models are doing a relatively effective job. If they don't, well, then we can go back and adjust those models, change the inputs into those models to better simulate what has happened based on that paleoenvironmental data. So we can use the paleoenvironmental data to test those process-based models. And then when we're happy with the way those models are operating, then we can simulate those future changes. And so the paleoenvironmental data becomes very important in developing sound models that can then be used in a management perspective for figuring out what are the potential changes to these systems from the inputs of climate change, from the inputs of mountain pine beetle, for example, on disturbances such as fire. So when we go out in the field, unfortunately we just can't go out to any particular lake and take a core. Our toolkit, and that's where I'm going to kind of focus the next little bit of the talk, depends on good selection of particular types of lakes. And so some of the things that we were looking for, and this is one of Vanessa's lakes, I think the furthest one that was on a map earlier today. One of the things that we're looking for is no inputs into those lakes. And so we don't want small creeks or rivers flowing into the lakes that could be bringing charcoal from much further away. We also look for relatively flat lakes. We want nice, simple bathymetry so that it's not a really complicated system to try and understand, and relatively small lakes as well. And so you may not call these lakes. People may refer to these more as ponds. This is one of the lakes that we'll actually go and visit tomorrow. This is Little Trefoil Lake, right near Jasper Park Lodge. And so these are the two of the lakes that we've been focusing on for this project. So how do we actually go out and collect these sediment cores? We've primarily been focusing on two methods. The first one here is a gravity core, and I'll explain kind of how these things work in a second. And this is what's referred to as a Livingstone piston core. And so this is from just last month, coring with Vanessa at one of her lakes, collecting a nice sediment core approximately about 1 meter long worth of sediment. So the way these things work, it's kind of along the same premise. If you had a straw and you put it in a liquid and you put your thumb over the end of the straw and then pull the straw out, the liquid stays in the straw. That's the same way these cores work. And so this gravity core works by just releasing or letting this thing down slowly through the water column, and then it gets down to the sediment water interface, And once it's down to that sediment-water interface, we have a messenger. And so it's just a kind of brass weight that we drop down along the line. And that brass weight contacts the head here, and when you contact the head, it releases this plunger that then goes into the top of the core. And so that's your thumb on top of the straw. And so at that point, then we can pull this thing back up to our little inflatable raft, and the sediment stays intact in the sediment core. And so we're able to recover that surface sediment. And so that interface between the sediment and the water, that then allows us to have a complete record going back in time. And so we assure that we don't miss any sediment and we don't miss any time in the past. The other type of core that we use is the Livingstone piston core. And so again, here is your kind of sediment. This is the bottom of the lake here. And so this has been driven down into the sediment. The piston's at the bottom, and so no sediment can go into it. And then we get down to the position where we want to core. And when we do that, we lock that piston in place so the piston level doesn't change, but then we can start to push the core down past the piston. And so as we push it down, the piston stays in place, but the core barrel starts to fill with sediment. And then again, we can pull that back out. It creates a suction and allows that sediment to be pulled out of the bottom of the lake. So that previous core, the gravity core, that will typically recover cores 50, maybe anywhere from about 30 to 60 centimeters long. So they're not really, really long. These will recover cores in 1 meter segments, and we can go down to usually in the range of 20 to 25 meters, depending on how much sediment is there and how much water is in the lake as well. Usually we're looking at 3 or 4 meters of sediment in the bottom of most lakes. And so we can iteratively collect all of the sediment that's contained in the bottom of the lake. So this is what we were doing with Vanessa. So here again is Vanessa's nice sediment core that we were able to recover from her lake. And then we could take this back to shore because it's a heck of a lot easier on relatively dry land. And we can then section these cores, and we can section these cores at relatively high resolution. In some instances, with some of the extruding devices that we have, we can sample at 1/4 centimeter intervals. Vanessa was sampling at 1/2 centimeter intervals for her work. So we can sample these at relatively high resolution, and presumably going back over relatively long periods of time as well. So what is in these things? You see these sediment cores, and they just kind of look like homogeneous mud. There's not a lot of stratigraphy to them usually, and so you don't really see a lot in them. Occasionally you do. But primarily what we're looking for in these sediments are all of these components that are coming in from outside, so the allonthinous material, and so that can be airly transported contaminants, for example, that get deposited from various sources. Pollen grains from the vegetation can get deposited on the surface and then eventually make its way down through the water column and get incorporated into the sediment as well. Soil particles from runoff, and so certainly when fires occur in an area with significant topography, that soil particle signature can be really important as well. And so it can talk about inputs into the lake as a result of fire, and we can look at the impacts of that as well. And then within the lake, we have the autochthonous material, so the stuff that's living and being deposited within the lake. And so that's primarily algae and other aquatic insects. And so for this project, we're primarily relying on these kind of airly transported things, so pollen grains and the macroscopic charcoal, and some of these soil particle components as well. And then the algae, which is what Katrina's looking at. So she's looking at these things called diatoms, which are these single-celled algae that live in these lakes and can tell us a lot about how the lake environment changes in response to fire. So just kind of an example of some of these things and what they look like. So the component from the atmosphere, so things like carbon particles from carbon combustion, fly ash from coal combustion, metals and other pollutants can be archived in these sediment records. And from the atmosphere as well, kind of this microscopic charcoal. And so at a more kind of regional or extra-regional scale, that microscopic charcoal, which we classify as less than 150 micrometers, that stuff will kind of fall into this category as well. From the catchment, and so kind of closer to the lake itself, we're getting things like pollen that's preserved in there, mineral particles that are being eroded and then brought into the lake, insect remains as well. And so there's been people that have been starting to look at whether or not we could find evidence of past bark beetle activity in some of these environments using lake sediment records. It's been not completely successful yet, but I think there's other ways to go about this as well, with the advent of biomarkers being incorporated into sediment analyses now as well. And then things like the macroscopic charcoal kind of fall into this kind of catchment level analysis as well. And then from the aquatic system, the diatoms. And so these are the things that Katrina's looking at, chrysophyte cysts and then chironomids. We're not looking at, but they can tell us a lot about how the lake environment changes over time due to a number of different factors in addition to just fire. So earlier, Zev had talked about some of the work that we have been looking at and trying to get at this idea of fire severity over long periods of time. And so this is some work from one of my graduate students, my PhD student, Colin Courtney Mustafi. And Colin has been looking at lots of charcoal particles in lakes. And as he was sitting there looking at them, he's also noticing shapes that would appear and would be repeated as he would be looking at these samples. And so he started to classify these into different morphotypes. And so we think that we can use these different morphotypes to find out what in fact was actually burning on the landscape. And so these kind of foliated, lineated, fibrous may be representing one type of material, these solid ones, probably more of a woody type material. Some of these here, probably needles or small branchlets, maybe roots. And as well, things like this may be representing needles from various plants. And then you get into things like this that could possibly be representing grasses. And so we think that in addition to just counting the amount of charcoal and looking at peaks in charcoal, we should also be identifying the morphotypes and the shapes of these different particles, because it may provide a little bit more information about the severity of these fires and what was actually burning on the landscape hundreds to thousands of years ago. So when we collect these sediment cores, and again, this is one of Vanessa's, and when you look at that, there's really no stratigraphy to that at all. There's about 1 meter of sediment there, and so you can kind of guess, I can kind of guess as to how old that core is. Sedimentation rates in that lake may be a centimeter may represent 5 years of deposition, maybe 10 years of deposition. So we may be looking at on the order of 500 to 1,000 years in that meter of sediment. But we can't say for sure.